Hi, everyone. Thanks for having me here today. As was said, I'm Laura, and I work for Oxide Computer. For those who haven't heard the pitch of Oxide, Oxide is rethinking the server from the ground up. Servers haven't fundamentally changed in many years, and Oxide is looking to change that. I promise this isn't just a sales pitch for Oxide, but the context for what Oxide is building is important for the issue we found and what exactly we need to do to mitigate it. One of the ways Oxide is rethinking the server is with a hardware root of trust. When I say hardware root of trust, this can mean many things to many people. And in this case, when I say hardware root of trust, I'm talking about a hardware root of trust for measurement. And this is answering the question about what software is running on the system. The theory here with the root of trust is that, okay, we're going to say, have our little hardware root of trust, it's got a ROM, it's got some software on it. We are going to trust that root of trust unconditionally. And then that is going to measure another part of the system. And then that part of the system is going to measure another part of the system until we've measured everything we want. And you get up an entire measurement about what's going on. This is done with a series of cryptographic hashes. This could be an entire talk all of its own. But the important thing for what I'm going to be talking about today is that you must trust your root of trust, otherwise everything falls apart. When it came time to select hardware for our root of trust, we had some pretty specific requirements. We need to make a strong assertion about the integrity and authenticity about what code is going to be running on our root of trust. There needs to be a unique ID to be able to do our measurement. And then we need a way to be able to extend the trust across all parts of the system and then be able to reestablish trust if other parts of the system become compromised. Other features you might think of, such as cryptographic accelerators, were considered nice to have, but not strictly necessary. Our requirements for the hardware root of trust led us to this LPC55S69 from NXP. This is a dual-core ARM v8M microcontroller which has TrustZone M and NPU support. If you're familiar with TrustZone on Cortex-A, it's kind of similar there. The LP55 has common cryptographic accelerators for SHA, AES, and doing field math. And the chip supports secure boot using RSA signatures. A couple features that I'll talk about later are there's a puff physically unclonable function and a feature called DICE, which is used to generate a cryptographically secure identity based on a secret and the running code. And DICE is a feature that really helps us to be able to say we trust what's running on our root of trust. So that's the hardware we selected, but of course we need software to run on this chip. And part of Oxide's philosophy is that you need to deliver software updates for all parts of the system. And this includes writing software updates for all of our microcontrollers. For those of you who haven't done this before, writing updates for microcontrollers is sometimes seen as a rite of passage because it's code somehow everyone seems to end up needing to write. Okay, so this is the memory layout of a theoretical microcontroller. You have your code running in Flash somewhere, and of course it needs to be updated. In this system, this microcontroller is often running out somewhere in the universe, maybe no way to physically access it. And what will happen is this device will receive an update over some sort of protocol and then write it to Flash, hopefully after checking that the signature is valid and everything. And so this also ends up meaning that the update code ends up running alongside whatever other code is running out there. A very common design for microcontroller updates is to split the Flash in half and has one part designated for the running code and the other part running as a secondary image. So when your update comes in, you're going to write the update to your not running space and then jump into that. This is also drastically oversimplifying how this update works. There's a lot of choices to be made about how exactly you do image versioning, what exactly is going to be checked. If you're doing encryption or anything like that, that's another layer of commentary. And so many ways this can go wrong and end up with a nightmare scenario of a brick device. So in conclusion, updates are a huge pain. And Flash is frequently the most resource-constrained system in a microcontroller, and so any code you have for handling updates is something that you could be using for like actual features people are willing to pay for. And this is where hardware manufacturers go, hey, what if we could solve this problem for you, software writer? What if we gave you code to do updates so that you could use your Flash for other things? Would you do more of our buy more of our chips? And this is where manufacturers like NXP offer exactly something like this. NXP has ROM code to be able to handle all these updates. The update code takes care of encryption, signing, erasing, all those hard things, so you as a software writer don't have to think about them. I went back and forth with my colleague when we were evaluating what to do for our update story about whether we should actually use this code, because some of my colleagues had had bad experiences. And eventually we came to the conclusion that, given we had so many other things to be able to writing in our system, it made sense to try and use this update mechanism. So the hardware manufacturer value add won out, and I didn't have to write update code. Okay. So let's talk about NXP's update format. This format is called SB2, which seems to stand for Secure Boot version 2. There's references to version 1 in this code, but I didn't look at it too closely just because it doesn't actually run on the chip. All updates are encrypted, and version 2.1 is both signed and encrypted. The unit of work on this block is 16 bytes, and this corresponds to encryption block size. On a resource-constrained system such as a microcontroller, you're not going to have enough space to be able to stage an entire update, so it's nice to be able to say, request 16 bytes to decrypt it, process it, and then go on to the next bytes. Okay. This update format has a 96-byte unencrypted header at the start of every update. This is followed by some HMACs for verification, a key blob for decryption, and then a certificate if it's signed, and then a series of data and commands to actually do the erasing and write the data for afterwards. Okay. This talk is mostly concerned with the header, which you're going to see here. This is 96 bytes. There's certainly a lot of fields here. But I want to highlight two of the fields which ended up acting as a magic numbers of sorts. There's this field 1, which listed as supposed to be STMP, and signature 2, which is SGTL. When I first started looking at this format, I was really confused about what these meant. They felt kind of random. And I ended up finding the clue to what I think was the answer on a 12-year-old wiki for running custom firmware on media players. Okay, this doesn't have a definitive answer, but I think this format seemed to come out of Sigmatel, who made chips for media processing. STMP was a product line of a particular set of chips, and SGTL seemed to stand for Sigmatel. Freescale bought Sigmatel in 2008, and then Freescale itself was merged into NXP in 2015. And NXP itself was a spin-off from Philips in 2006. So this format has been around for a number of years. And the answer to why exactly we seem to be using this format is silicon vendor consolidation. And by the way, if anyone happens to know anything more definitive about the history of this format, I would actually really love to know. Okay. I mentioned that SB2 updates are signed and encrypted, which also leads to the question about where are these keys coming from and how exactly are you trusting them? The LP65 splits its flash into two parts. There's user flash for your user programs and the protected flash region for various configuration data. There's a dedicated region for storing keys, and all the keys are puff encoded, which means they can be safely stored in readable flash. The key store stores several different keys. The important ones for this talk are the SBKEC Secure Boot Key Encryption Key, which is used for decrypting updates, and the UDS Unique Device Secret, which is used with DICE to generate the unique identifier. The CMPA, Customer Manufacturing Programming Area, holds things like secure boot settings and the hashes of keys for verification. The CMPA can be sealed to prevent further modification. And once the CMPA is sealed, you can't change any of the values of the generated key, you can't turn off secure boot, and you can't change the hashes of the keys. Okay, so this update format looks reasonable. It seems like it's secure. But it turned out, when I started to try and actually look and do something about this, it really honestly seemed kind of complicated. There are a lot of different fields there and things to get right. And I'm not saying this entire talk is the result of me not wanting to try and figure out how to parse this update, but it's kind of close. More seriously, this format is used on our root of trust, and I'll say this several times. If the root of trust is broken, everything else about our measurement is broken. And I think if you've looked at software at all, you know, parsing is one of those places where bugs are absolutely abundant. And the question here becomes, how much do we trust the ROM to actually parse this update format correctly? And honestly, we had very good reason not to want to trust the LPC55 ROM. I found an undocumented hardware block in this same chip that could be used to be able to violate privilege boundaries. I spoke about this with my colleague Rick last year at DEF CON. And after we found this issue with the ROM patcher, we went back and forth about whether it made sense to continue using this in-ROM update mechanism. And we came to the conclusion that, yeah, it did make sense just because we thought we understood how the ROM patcher worked enough that we could successfully mitigate it. But, of course, that doesn't mean I wasn't still curious, and I still had this ROM dump lying around to be able to continue looking at exactly how this ROM was parsed. Okay. So, I've mentioned NXP's boot ROM. NXP's ROM is the very first code that gets run on PowerUp. It's responsible for things like power settings, verifying signed images, and everything like that. I could probably give a full talk on NXP's ROM at this point. It also has entry points for things that can be called at runtime, like flash, writing to flash, and calling update code from user code. The ROM uses SRAM for holding all of its global state, which will be important in a bit. Yeah. The ROM also has a mode called ISP, or in-system programming mode. This is a protocol that can run over various hardware interfaces to be able to run a fixed set of commands to do things like write to flash or configure fuses. Importantly, when in ISP mode, the LP55 is responding to what's being sent. It's a packet-based protocol that can send up to 512 bytes at a time. You can send less, but 512 is the maximum. This ISP mode is designed to be orthogonal to being programmed via debugger, and when you're in ISP mode, you are not supposed to have access to either JTAG or SWD. And also importantly, when the CMPA mode is sealed, i.e. you're not supposed to be able to change any of those settings, the only way you're supposed to be able to make changes to ISP mode is via a signed SP2 update mechanism. Definitely not ominous there. Okay, so this is a pretty boring diagram about what it looks like when the LPC is in ISP mode. It's sitting there executing commands in ROM. If we want to do an update, we'd send the command to be able to start an update, and then send the update 512 bytes at a time until it's complete. Okay. So let's look at how the update is actually parsed. All the parsing state is stored in a 752-byte global variable in SRAM. Okay, there's 752 bytes worth of fields. I'm just going to focus on some of the more interesting ones. The first here is this 16-byte array. The parsing loop, which I'll show shortly, will copy 16 bytes at a time into this global state. The second interesting function here is this callback function. The parsing state machine works by calling this callback function on each of the 16 bytes. And each function is responsible for updating the global state to set the next function to be called. If the global state does not get updated, the same function will get called on the next 16 bytes. Okay. Here's a sample of what the initialization looks like. Nothing terribly interesting, a mem0 and then setting the first function. And then here's an example of what the main update loop looks like. We're going to copy the 16 bytes of data from our input and then put it in the global array. Again, this is pseudocode. There is, in fact, more actual error handling in the ROM, but this just gives you an idea about what this is doing at the high level. Okay. And, okay, this is a screenshot from my annotated disassembly in Ghidra. And this is the very first function to start parsing the header on the first 16 bytes. Bear with me on any of the names and other things like that. This is a little bit like looking in a lab notebook at all my scribbles. Each callback function takes an argument to this 752-byte global header as an argument. And so when we look at this, we find another field in this header another field in our global state is this 96-byte header. And so what this function is doing is setting up a pointer to the start of this header, copying over the 16 bytes we previously did, then incrementing it, then setting a callback to the next function. And this pattern of copying bytes and incrementing the pointer is going to be common to all the functions we see. And this is just a sample about what our header actually looks like, global state actually looks like now. We still have the callback, our copy data, and our 96-byte header. And this is part of the second function. You can see there's the same mem copy and increment pattern, but this is also an example of where things start to go wrong. I mentioned that this update is signed and encrypted, but this header is not signed or encrypted, and at this point in time, it's literally just receiving whatever bytes we receive, and this is completely untrusted input. And here we see the parsing code just subtracting 2 from whatever we put in, which can result in an integer underflow if you give the wrong value. I should note, this was one of the first things I found when I started looking at this header, but it didn't really get me anywhere except for later triggering some errors in the error handling code. But again, if you see one integer underflow, it's a good sign that there are problems looking elsewhere. And we get to the third floor, and oh yeah, there's another integer underflow. Whoops. And we get to the fourth function, and okay, there's an integer underflow, but also importantly here is that this value that's being stored is again coming straight from the header and is untrusted input. Okay. And we get to this fifth function, and if you look at this function again, you'll see our usual pattern of doing the memcopy, doing the increment. But you also may notice that we're only updating the callback in this if function. And so this means that until we actually get to this if function, we're going to continue just doing this increment and memcopy. But you may also notice carefully that the value in the if condition is the value that came from the header, which is untrusted input. And you'll probably see where this is going. This ends up being a buffer overflow. If we set that to a sufficiently large value, we'll just continue copying bytes outside of our buffer, which is supposed to be our 96-byte header. Okay. Buffer overflows are cool, but ultimately the question is, what exactly we're going to do with this? If I'm an attacker, I want to get code execution. And so we start looking around about, okay, what else is outside that we can overflow into? And after our global state, there were a couple of interesting global variables related to heap allocation that turned out to be pretty handy. Okay. The ROM generally doesn't make use of dynamic memory allocation. Everything's pretty much stack allocated. The places where there are dynamic memory allocation is mostly related to keys and cryptography, where things may not be known at a fixed size. And I think also some of this is a fallout from the library used for cryptography in the ROM. Seems to be a fork of embed TLS as well. So to be able to accommodate this, the ROM includes a very simple bump allocator that that allocates from the start of a global variable that exists literally right after our 752-byte global parsing state. And also incredibly conveniently, right after we complete our buffer overflow, there's this heap alloc call as well. And in the very next function after our heap alloc call, we're going to do a memcopy of our header into this new allocated buffer. Some people may be wondering, okay, why is the code bothering to do all this copying and allocating at all? And this is because this is related to the signature verification. And the code for signature verification on updates is the same as the code for signature verification on boot images. And this requires everything be in one contiguous walk. And signature verification also relies on an X509 certificate for holding the public key. And X509 certificates are not going to be a known size, so heap allocation is the only way to be able to get enough space. Okay. But back to breaking things. Well, okay, so what do we have so far? We know that we can overwrite the address of where the heap starts. We know that there's a heap out call right afterwards. So how do we combine this to actually get code execution? And we actually already have a clue already, and it turns out to be this callback function that I've mentioned for all the parsing. The callback function lives at offset 4 from the start of our global parsing state. And if we happen to look at the same offset from the start of our header, it's supposed to be used for the nonce. But it turns out that because we found this issue before we've gotten to any kind of decryption, we can go ahead and just put whatever we want there, like, say, an address. Okay. So putting all these pieces together, here's how we're going to get code execution. We're going to craft a custom header with this key blob block calculated to how much we want to copy outside of our bounds. At offset 4 in this header, we're going to put what address we want to jump to. We're going to pad out our header to what we want to write to the start of the global structure. And after we finish writing our structure, it's going to do the memcopy, which is then going to trigger the next time in the loop, it's going to execute the function. Okay. And for a little bit of a different visualization, this is our global parsing state, and right after it it's our heap state. We're going to do a buffer overflow, overwrite our heap state, for that address, which matches with the start of our global parsing state. So when we do our mem copy, we're going to copy our SB2 header, which has our carefully calculated address, and it's going to execute whatever value we want from the header. And this does give us code execution, but not full execution. This lets you redirect the PC to code in the ROM, because one of the very first things the ROM actually does is enable MPU and SEU protection, and this restricts execution to only specified region of memories. And I should be clear here, I think this is a very good thing. This is a fantastic defensive measure to have enabled. I mean, at least this is what I tell myself when I'm not the one trying to get code execution. But of course, nobody ever, got code execution by giving up. The MPU restricts execution to specific regions of memory, so it's always worth asking if there are other writable parts of memory that are also executable that we could perhaps leverage. And it turns out the answer to this question is related to the previous work I did with the ROM patcher. The actual purpose of the ROM patcher, when it's not being used to violate security boundaries, is to be able to fix bugs in the ROM. It does this by either doing a straight word replacement in the ROM or by inserting an SVC instruction. Typically, the SVC instruction is used to be able to go from a less privileged mode to a more privileged mode, but it also turns out that it's a pretty convenient way to be able to go and inject a series of code that you want to put at a specific address. And since the point of the ROM patcher is that this patch code does not live in ROM, it must mean that there must be some point in writable memory that's also executable. And it turns out that the area of memory where the executable lives is right at the end of SRAM, where we're going to be buffer overflowing. Okay. So this means that the solution to our problem is to do a very long write across the global state. So instead of stopping when we get to the heap state, we're going to keep writing until we actually get to the executable ROM patch area. We're going to be writing over an awful lot of our global state, but it turns out that most of the stuff there we don't care about, and because we can control the data, we can also be able to select what actually gets written there. And as I was working through this issue, trying to get this to work, this was working pretty well until I got 232 bytes from the end, and I basically ran into a wall, and it stopped. And this is because the LP55 ROM has stack canaries. For those who haven't seen this defensive attack before, the idea with a stack canary is to be able to catch stack overflows. So at the start of your function, you're going to write a random known value to the stack, and then at the end, you check if this value is still the same. If it is, you're good. If not, you panic or do some sort of other error handling. Okay, I should reiterate again. I think seeing stack canaries is a great defensive measure. Always make it harder for everybody to be able to do exploits. But again, as an attacker, it's certainly a pain. And some of you may be wondering, okay, the buffer overflow you showed before is a global buffer overflow, not a stack buffer overflow. What's going on here? And this is related to the particular implementation of stack canaries. If you've seen stack canaries on a larger system such as x86 or ARM64, they will frequently store the stack canary in a dedicated register just because there's enough register space. But on a smaller system such as this microcontroller, there's not enough registers, so the compiler ends up putting the stack canary in global space. So what's actually happening is that we are overwriting the stack canary in the global space, and then when it goes to check it again later, that's when it's detecting. Again, I don't think the stack canary was intended to be used this way, but this turns out to be a pretty good way to be able to detect global smashing as well. Okay, but there turns out to be a workaround for this as well. It turns out that the stack canary itself is not detected in the update parsing mechanism. It's only detected in the ISP parsing mechanism. And so what it is that it's only when we go to get more bytes from ISP mode that we actually detect this issue. So the workaround here ends up being we do a write right up into the stack canary, and then we overwrite the stack canary and get the executable ROM area in one 512-byte write. And this ends up being really lucky for us because these two happen to be close enough together. Okay. So putting all of this together, we're going to have our custom header with an out-of-bounds field saying how much overflow we're going to do. One of the fields is going to be the address we're going to execute. That's going to be our executable SRAM area. We're going to do our buffer overflow, and we're going to be sending all of these bytes over ISP mode, 512 bytes at a time, until we get right up to the stack canary. And then we get to these last 512 bytes, we're going to overwrite the stack canary and get the executable area. In our executable area, we're going to put just a small payload to be able to turn off the MPU and SAU, and this will enable us to be able to jump wherever we want. Okay, that's a lot of things, and now I'm going to attempt to do a live demo. Actually too big. I bumped up the size anticipating it was going to need to do that, but apparently not. Well, I love software. Yeah. Okay, I'm going to skip the demo. Sorry about that, but I will be around afterwards to be able to potentially show this afterwards. Okay. My previous job was working on Fedora desktop, so this is a little embarrassing as well. But okay, I promise that what I was going to demonstrate was just a little show about being able to go into ISP mode, being able to access that, and what exactly that looks like. Mostly to be able to show exactly what the header looks like, and be able to dump a couple of key registers to be able to show, so it looks different when you have something on there versus not in there. But okay, but there's definitely an exploit. And the question is, what exactly can this get you? When you can get code execution when you shouldn't be able to. You can read out of the flash if you want. I should emphasize that. As far as writing, I also like to start with what this can't actually get you. You can't actually unseal the CMPA or NPA. This means that if you sealed, you can't actually change what the secure boot is enabled. You can't change the keys that are used for secure boot verification. And this also means that anything covered by secure boot can't be changed. So again, what can you do? Definitely read everything out. You can execute changes, execute code. As far as persistence, any flash pages that aren't covered by a secure boot region are fail gamed. You can do a rollback to a known good signed image. There's also some potential denial of service vectors. Certainly more if you want to get creative. And I should also emphasize that if you're running with an unsealed device, basically you're pretty much out of luck and the device should be considered completely compromised. As far as what Oxide is concerned about, the most concerning for us is related to DICE. I mentioned this before as a feature for generating an ID. DICE stands for Device Identifier Composition Engine. This was a feature designed that originally came out of Microsoft that is now part of the Trusting Computing group as a specification. It's designed to be able to tie a device's identity to both a secret and the running code on the device. And this ends up giving us some really nice properties for being able to do measurements. Very importantly, the device secret must be kept secret. Exposing this secret could allow another device to pretend to be our root of trust, which, again, would be pretty bad for what we're trying to do with trusted measurements. And to make sure the UDS stays secret, it's encoded by the PUF. PUF stands for Physically Unclonable Function and takes advantage of randomness in the SRAM cells on the chip to create a fingerprint unique to a particular chip. We can take data that we want to encode, such as a device secret, and combine that with a chip fingerprint and an index to get a value that can be safely stored in flash. This means that even if you read out a value that's been PUF encoded, you need to feed that device back through the PUF on that particular device to be able to get back the value. Okay. And to make sure you really can't get access to the UDS, the ROM locks access to the key index used to encode the UDS. This is what I was going to dump with the demo. But this is the key block register for the PUF. There's a lot of different fields here. What's important here with this value is that the top bits are saying this entire register is locked and can't be changed until the next power up. And the 6 there indicates that key index 15 corresponding to the UDS is locked. But it turns out at this time we do the exploit, the UDS itself has not actually been locked, and which means that we could potentially read it out and read out this unique device secret. I should also note that not having this locked at the point we're doing this exploit isn't necessarily a bug with the UDS itself or DICE. It's really a consequence of how DICE works. We need the hash of the running image in order to calculate our final DICE value. But of course, at the time we're doing this, we don't actually have the image value because we're doing an image update. I can think of some ways you could potentially work around this, such as locking access to the UDS before you actually do a software update, but that also has some other implications for how ISP mode potentially works, and there's a lot of things you might need to sequence there. But, okay. So, this fix is kind of bad. So the question is, what exactly we do to try and fix this? All this code is in ROM, so any actual fix is going to involve new hardware. But thankfully, we find ourselves living in a time with plentiful silicon and definitely not 100-week lead times. Okay, less sarcastically, I should make it clear that NXP did agree with our findings and agreed to deliver a fix. But even in the best of circumstances, delivering a hardware fix is going to take time. And Oxide is still trying to ship a product. My actual job is writing firmware, not just finding bugs in chips. I am grateful that Oxide does see this work as valuable. I think everybody should feel confident telling their boss they got code execution instead of working on anything else that will actually bring in revenue. But I will also say that the novelty of finding bugs in this particular chip has really worn off. This is the second issue we found with this chip, and this is very important work, but it really does take time away from shipping a product. And usually at this point someone goes, okay, you found 2 CVEs, why are you still using this chip at all? Which is a very fair question. We selected this chip back in spring 2020, and we still have all our internal notes about what we did why we selected it. And it turns out even back then, there were a fairly limited number of chips that met our requirements. And even before we ran into the silicon shortage, we ruled out a non-zero number of them simply because we couldn't get hands on hardware. The only thing we could get were data sheets. Okay. After we found the stuff for Overflow, we did seriously consider trying to switch to a new chip, but at least for now, we've decided against it. At least for, among other reasons, because we know the LPC55 all too well at this point. Introducing a new chip at any point in a product cycle always brings in risk, and that would involve, a new chip would involve having to redo all of our software work and all of our hardware integration work we've already done. And there's no guarantee that any chip we chose would actually be better. It could have even worse bugs or flaws. And this is, of course, assuming we could even get our hands on silicon that we actually wanted. So until we actually get fixed chips, we're stuck mitigating these issues. When it came time for mitigations, a couple of different issues got thrown around. If the issue is just that the header isn't being validated, could we validate the header ourselves? And the answer there is theoretically yes. If you treat the SP2 update functionality like a function such as memcopy, where you need to get all the arguments right, you could catch issues with the SP2 update. But the question then becomes, what exactly is doing the validation? And this ISP mode involves having another target send data, and so that would involve having another target do our validation, which is the opposite of what we want for a root of trust, where we want to say, okay, we want to trust this small amount of code and hardware as possible. It is possible to invoke the update code from the chip itself without actually using ISP mode. This could potentially allow us to validate the header and check and also check the signature. Checking the signature is something that NXP recommends for a workaround for this, but I think it's also important to remember what signature checking actually tells you. A public key signature verification will give you authenticity guarantees, but will not tell you anything about whether that data is actually correct. I've certainly signed some bogus code for testing when I've been doing my development. And I realize what if someone signs some bogus code is a fairly specific threat, but Oxide is building something fairly specific, and it was something that was worth considering from our perspective. Okay. But let's say that Oxide did decide that we want to check the signature. I ruled out using ISP mode, which means that we're going to invoke the update code from our own flash. Okay, this means since we're now doing in Flash, we're probably going to have to do something like, say, splitting our own Flash in half, and we're going to have to come up with a way to be able to send the data back and forth, and then do image versioning, and wait a minute, why exactly are we doing all this work to be able to use a potentially buggy API? And this brought us to our final conclusion that while the update feature would have been really nice to use, it loses a lot of its value if we have to do all this validation ourselves. And it turned out to be much easier for us to be able to write our own update mechanism rather than try and force an existing one. And this is where the title of this talk, Unwanted Features, comes from. If your update mechanism can be used to get code execution, it's not a feature your customers are going to want to run, which is kind of unfortunate. Okay, some takeaways here. Validate your input. This is kind of obvious, but it's really worth reiterating that you need to carefully consider your security boundaries. And even especially for code which has been around for perhaps, tens of years, like this format is, you've really got to think about what else might be there. And fixing ROMs is even harder than fixing software, so you need to be doubly careful about how exactly your ROM is validating input. There's an argument to be made that the correct amount of code to have in your ROM is 0, because you can't have bugs if there's no code. And I realize this may be an unrealistic proposition, so I go for something a little bit different and say that if you're going to be delivering ROM in your code, you should also be delivering source code that can be audited by anyone. Chip makers like NXP come up with these hardware features because customers are asking for them. I don't want the takeaway from the talk to be that all ROM features everywhere are completely useless. I don't think that's true. But the thing is that a lot of people are reluctant to use them just because they've had bad experiences with them being buggy. And delivering source code for your ROM is no guarantee of correctness, but it's a good way to help convince your customers that it is correct and they will want to use it. Several things need to go right or wrong depending on your perspective to be able to turn this buffer overflow into execution. Having the MPU on was a very good thing. Having the stack canary is also a very good defensive measure. I think I got really lucky with the layout of the global space. You might have had to get more creative to be able to work around that. You should always assume that someone is going to be able to find a bug and make it hard to be able to do anything with it. And there's not one single approach for mitigating an issue you found. Like I said, Oxide is building something very specific. It made sense for us to be able to take the most cautious approach. If our entire product was based around the LPC55, we might have made a different choice. In an alternate universe, I could actually imagine that we may have run into other unfortunate delays, and it might have given us enough time to be able to swap out the LPC55 for another chip and be able to integrate it that way. Again, there's so many different possibilities. Ultimately, it comes down to thinking about what's your product and what is it trying to accomplish and what's going to be best for your customers. I don't wish chip bugs on anyone building a product, but I hope this has been some food for thought on my experience. So, thank you.
Do we have any questions? You can bring the mic. Okay.
Was the stack canary value chosen randomly at runtime, or was it fixed?
That's a good question. The stack canary itself is randomized at runtime, and the stack canary is actually implemented as a ROM patch feature as well.
Okay, thank you.
Any last question? Okay. Thank you, Laura. Thank you. Okay.